Pronto. Good afternoon, everyone. Today, Ricardo will talk about the Seesaw mechanism type 1. So, let's start.
Hello everyone, good afternoon. As OCS said, I'm gonna present. Can you guys see? Please.
Yes, we can.
Okay. So I'm gonna talk about the type 1 cell mechanism. No? It's here live. Okay?
Deve começar em algum momento.
Okay. So I'm talking about the Seesaw mechanism type 1. I'm gonna start discussing some brief remarks about the neutrino oscillation. So the idea of the neutrino oscillation is that the neutrino, any flavor of the neutrinos, as it travels through space, it oscillates in another flavor of neutrinos. So you have here the flavor states, the mass states of the neutrinos, and the PMNS matrix. Okay, so the neutrino can oscillate. The probability of oscillation of this neutrino is given by this. This is the probability of oscillation between two flavor states, but you have between the three of them, but this is the simplest form. So you have here the theta, which is the mixing angle. You have the mass splitting, which is this delta m squared. This L is the distance that the neutrino travels before it oscillates for this probability, and this E is the energy. Okay, so this is the mass splitting, and you have here some data of the discovery of the Super Kamiokande, one of the detections of the neutrinos. In this case, is the mu neutrino transforming to the tau neutrino, and as you can see, you have a non-zero mass splitting here around 10 to the minus 2 or 10 to the minus 3, and you have a sine of theta, which is approximately 1 or 0.8, so it's not zero. This probability exists, and this means that there should be a mass difference between the neutrinos, and if you have oscillations, as the data says you have, then you can prove this data using the neutrino oscillation hypothesis, and this means that the neutrinos should have mass. Okay. Another important thing to keep in mind is the mass scale of these neutrinos. In the right side, you have the fermions, excluding the neutrinos of the standard model. So they are in this regime here of the MeV or GeV mass spectrum around here, and the neutrinos are far below. Okay, so you have this gap of mass scale. There is no particles, and the idea of the Seesaw mechanism, one of them is to expand the standard model with more particles, and those particles helps to explain why this mass of the neutrinos are so different from the other fermions of the standard model. Okay, so I'm gonna start with the Dirac equation, which is given by this. You have the Dirac mass here, md, and the spinors. So if we expand this mass term here in the chiral basis, you have this form. This is left-handed chirality, right-handed chirality, and they interchange between them. This term here, if you're considering, for example, leptons, it conserves lepton number because, for example, if this is a positron and an electron, you have a lepton and an antilepton. So if you sum the numbers of leptons, you have 0. Okay? And you can organize these terms in a matrix form, which is given by this. Okay? Just an organization form. Okay. So now I'm going to talk about Majorana mass terms. So you have here a Majorana term. In the first case, we used those types of terms to create mass terms. And this Majorana term is terms like this. For example, this term like this, which means this C here represents the charge conjugation of the field. So you can create those other kinds of fields which contributes to the Majorana term, mass term. Okay, one of the characteristics of this charge conjugation is the change of chirality of the fields and the change of particle to antiparticle. So when you operate this charge operation, you get a particle becomes an antiparticle if it's a particle, and the chirality if it's left becomes right. Okay, this is just because of this property here. C gamma 5 equals minus gamma 5 C. Okay, so when you operate and commute the C with the gamma 5 of the chirality operators, you have the change in chirality. Okay, so it means that again, when you're constructing a mass term, you use this notation for any fermionic field. You can separate the fermion in the left-handed plus a right-handed chirality. Okay, but if you are dealing with a Majorana particle, you can, instead of using, for example, if you have only left-handed field, in the case of neutrinos, for example, you don't have a right-handed one in your theory. So in order to have this type of form, you can generate the other chirality applying C, the charge conjugation, in your left-handed chirality field. You get this field here, which is right-handed, and the condition for the field to be Majorana is this one. So this becomes phi again, and you have the other chirality. So only using the left-handed chirality, you can generate this term here as we showed in the Dirac case, but this is a fermion, so you can generate those kinds of fields. If you have a left-handed chirality, you charge conjugate it into a right-handed field. And if you have a right-handed chirality, you charge conjugate it into a left-handed field, which is the second case here. So you can construct those two kinds of spinors. And any one of those you can show, it can be described by this mass term. This can describe this mass term. And this mass term has a mass L for left-handed, because you have left-handed here, and the left-handed apply the charge conjugation, becoming a right-handed, and so on. And the right-handed, the same thing. So you have a right-handed mass in this sense, but it's not that, but it's a mass for those kinds of terms. Okay, and again, so you can combine the idea of the Dirac masses, is those ones that I showed before. These terms here, the second one, which is left C, right C, it becomes right, left. Okay? Because you need to have left, right, right, left here. So those C transforms into this other form. And you get back the Dirac term that I showed before. And those other two are only those Lagrangians here that I showed above. So you have Majorana mass terms and Dirac mass terms. And you can write it in matrix form, and it gives this mass matrix here, and these states, left-handed states and right-handed states. Okay, and the Hermitian conjugate. Okay, so the model that I'm, oh, okay.
Can you go back one slide? So, I mean, this notation is what you explained there. You are conjugating the C and the R. It's outside, or is it?
This using this notation. So if you have this field and you apply charge conjugation by this, you get a change in chirality. This one. So you apply C directly into the field. And the chirality is like operating outside.
Okay, no,
The
it's
operation.
because you wrote.
And this notation here is the C inside.
Okay,
Is that notation that you're talking about?
yeah, because you wrote that last line and I was confused.
Yes.
No, the one below it. Yes, this line and I was confused.
Mhm.
It means the same thing.
No, it's just if you operate.
The C is outside, right? Outside everything.
No, it's inside.
Oh, okay.
It's inside. It's the notation.
So this PC psi, the psi CL is exactly the one you wrote there, right?
This one?
No, that one.
This?
Yeah.
No, it's outside. This is outside, this is inside.
But why is it R there?
What I'm asking is this. So let's write this explicitly. So this you mean this? That's what you mean?
No, they are inside.
Okay, so you mean this.
Yes.
Then why is it R?
Because okay.
It takes it out.
It's not the same thing. No, this
So
one.
the psi CL psi CL is equal. So if I
Okay.
place this charge conjugation of this one,
Okay.
so I get psi L, and then this is psi CR is equals psi R equals psi L C. When it is, yeah, so this is correct. This thing's correct, and this one.
Correct.
Yes, you're right.
It's correct. It's a property. You can open the charge
Yeah.
conjugation operations and show it.
It's applying this with the.
Psi C L outside.
Okay. Understood.
They in some way cancel the charges
Okay, like you get the
And-
charge outside
and they
it
change the
cancels.
chirality.
Okay.
Is a property. But you can prove this. Right here. Okay. So now for a case with descendant model particles, which in this case is the three neutrinos, and a right-handed neutrino. Okay, you can have three right-handed neutrinos, but in this case, I'm going for the simplest case. Okay, so in this case, you have the active neutrinos, which is the left-handed component that we are familiar with. We apply the charge conjugation in it, and you have a right-handed component from the left-handed chirality of the neutrino that we know. Okay, and you have the stereo neutrino, that is the neutrino that doesn't interact through the weak interaction. Okay, so it doesn't interact like this one, and it is given by this bigger N, and it's a right-handed one, and you can charge conjugate it into a left-handed field. Okay, so you have right-handed and left-handed for active, and right-handed and left-handed for the stereo neutrinos. now you have those equations. It's the same thing that I showed you before, but in the case instead of using psi, I'm using the neutrinos, the nu, and instead of using psi r, I'm using nr. Okay, so those are the matrices, and what we should do to it is diagonalize this matrix and find the states, the mass eigenstates of these vectors. Okay, so applying this transformation here in this form, you can find that this matrix, applying those transformations, you can force it to be diagonalized if you use the eigenvectors of this matrix to form this U matrix. I'm going to show you after. So the condition that we are going to use for the Seesaw mechanism is this one. The ML mass is going to be 0. So here it's going to be 0. And the mass, right-handed mass, is much greater than the direct mass. This is a condition. You can choose other conditions, but it's not going to give you the Seesaw mechanism. Okay? The eigenvalues of this matrix here, using this condition, is given by this. So you have eigenvalue of the mass, right-handed mass, and minus the mass of the direct mass squared divided by the mass of the right-handed mass. Okay, and the matrix diagonalized is obviously this one, and the transformation is given by this. Okay, so those here are the two eigenvalues of this matrix. Okay, so the spectrum is divided into a heavy neutrino of mass mr and another light neutrino of mass md squared over mr. And this is the Seesaw mechanism. What do I mean? When you have, for example, a large mr mass, here you have a small term, this term here is small, and you have a small mass of 400 neutrinos. So those mass here are for this term, this complete term is the light neutrino, and this term here is the mass of the heavy neutrino. Okay, so when you put the mass of the heavy neutrino to very, very large scales, it decreases the mass of the light neutrino. So I gave here an example of the mass scale. So if you consider, for example, that the mass of this neutrino is 1 eV, which we know that the sum of the mass of the neutrinos is 1 eV, so it's lower than that. And we consider that the direct mass is of order 1 GeV, which is like the order of the electron mass, and so on. Then we get that the mass of the right-handed neutrino should be of this order, 10 to the 18 eV. Okay, you can do this mechanism for one neutrino or for the 3 neutrinos. The only difference is that instead of this 2x2 matrix, you will get a 6x6 matrix. Okay, so it's to give mass to the other neutrinos and to generate those terms. And for any neutrino that you want to have mass, it's gonna have a right-handed component to using this balance here to change the mass of the neutrino, to put the mass of the neutrinos in lower scales, and those right-handed neutrinos components going to high scales. Okay, so that was my presentation.
Actually, it's possible to do the Seesaw mechanism, but only two right-handed neutrinos.
Yeah, one of them could be massless. Yeah.
Could you give us a signature of the type 1 Seesaw mechanism?
No, I don't know this part.
The next part is projected in YouTube.
No, it's not possible.
So let me end the screen.
Alguém falou alguma coisa?
Oh, there are any questions? Pode falar.
Aparecer em YouTube, né?
Não, é só cancelar o YouTube.
Can neutrinos be at rest?
In what sense? Non-relativistic?
Yeah, at rest. Because you said that neutrinos oscillate when they are traveling. But what if they are at rest?
But are you asking about if it's possible the neutrinos decay?
No, é só something.
No, at rest, no velocity. Velocity, sorry.
Is there a reference?
Yeah, I think you can go to this reference frame or
As long
So-
as they're massive.
yeah, if they are massive, you can go to this reference frame.
Okay, so they oscillate in the reference frame.
Yeah.
It's not just a question for you, it's for anyone who knows. Because I I asked it in the Google said yes, they can be at rest. And then I asked it to DeepSeek said that they can't be at rest. So
Who knows that?
I think the probability depends on the.
Yeah, the probability depends on the travel distance.
Exactly.
So it's a sign. So it's a sign of zero. The probability is going to be zero if it doesn't
You are in this-
change the position.
Exactly.
So the neutrino itself cannot see
Like-
itself changing the flavor.
Yeah, but I mean,
Yes.
this is a question about reference frame, right?
Reference frame, yes.
And the neutrino is not actually at rest. The neutrino cannot be.
No, it can be.
If it's not light,
It cannot rest it.
That's
Forever
relative.
rest.
If it is massive,
yeah, if it's not light, you can go to a reference frame there where it's
The
it's
answer-
it's
the answer is what
it's
it is.
that's that.
it's only
The neutrino doesn't see itself.
they
Yeah.
can't see itself.
Yeah,
So you have
it means
here-
that if you go to a reference frame,
So
neutrino-
if it doesn't
No,
evolve in space, the probability is going to be zero here from this
To
equation.
go to another flavor, but it will always see, it will always go to the same flavor. Something like this, because
Yeah, it's going to remain in the same flavor, so it doesn't oscillate. So you don't have oscillations when it's stationary.
it's trivial.
Okay,
Finaliza o YouTube.
how do I do this?
Aí, end the screen.
And string in the corner right.
It's